Yeah, okay. So thank you everybody for joining today. It's really my pleasure to welcome Mario Cuoco in this Orbitronics seminar series. So Mario is a researcher at the CNR, which is the National Council for Research in Italy, and is currently located in Salerno, right?
Yes,
Okay,
yes.
wonderful. And so he's going to tell us about orbitronics in superconductors, and we are very much looking forward for your presentation. So, Mario, the stage is yours.
Yeah, thank you very much, Aurélien, and thanks everyone joining this seminar. So yeah, I'm happy to share with you kind of overviewing of results we got recently and on superconducting orbitronics. I didn't know who was going to attend the seminar, so I will try to be kind of general, but of course you can interrupt me anytime if something is not clear. Okay, so my goal today is to show you several effects which can be obtained in a superconductor when you take into account that your electronic structure have a non-trivial orbital degrees of freedom active at the Fermi level. So this is actually also the key topic of the project led by Aurélien on orbital electronics. And here, but now it's more on superconducting states. So I will basically surf around these things I'm putting here. So I'm not sure that I will be able to really show everything, but I also really wanted to give you as much as possible a general flavor of what you can get. I mean, when you try to include these degrees of freedom in your view of superconductivity. Okay, maybe I start very smoothly with the motivation, but most of you they know that why orbitals can be really interesting or useful. That you can use we want to use orbital angular momentum, but I will tell you that maybe there can be something more. I mean, the one can dream that you can have, of course, more functionalities using orbital ordering, coupling to the lattice. I mean, this is interesting that you can use phonons. Maybe there can be higher coherence coming from the lattice. Orbital correlation can be more robust than other degrees of freedom, quantum degrees of freedom. There are high impact issues on sustainability. You can maybe get new phases, and I will try to convince you that there are new phases you can drive. And one thing which is also probably very promising is that all these things, orbitals, naturally is charged, talks to electric field. We may aim to get something which doesn't depend on magnetic field. Okay, if I start very smoothly, I mean, what are the players in our crystal is charge, spin, orbitals. Okay, I want to be very clear from the beginning. Orbitals, I mean, if you don't think about the crystal, electrons are around the atom, they have these orbital degrees of freedom. We know all these orbital wave functions, but there are also another orbital degrees of freedom, which is when electrons, when you take this periodic potential, they are block states, there's a Berry connection. So your electrons, they can have a rotation, which is in, let's say, let me put this way. So I mean, if electrons goes around with many atoms in the crystal, you have to think about this Berry connection, Berry curvature of your block states. And when you look at something which is close to the atoms, I mean, at the end you will also find, I mean, what is coming from the rotation of your electrons, I mean, of the atomic part of your. And in the remaining of my talk, I will mostly use this local picture, but of course this concept can be also generalized to this Berry part, which I think is very challenging in the context of superconductivity. So there will not be much time to enter in that, but it's definitely is a direction to explore. Okay, so these are orbitals in electronic states. I mean, there are two key concepts. one is quadrupole. So let me put that in a language which is a little bit more, is a little bit different, and I want to touch something which is also new, I would say. So when you take charge can be quadrupole. This is on the left side of the screen. Or it can be dipole. This is on the right side of the screen. And of course, I mean, okay, these are quadrupole. There can be also multipoles. Depends on how much is the angular momentum, right? So these two objects, I mean, respect to the spin, they give the richness of the orbital degrees of freedom because spin 1/2 is only dipole. So orbitals can be quadrupole, multipoles, and they can have also angular momentum. These two things, if you are in a limit where the crystalline potential is very strong, you think that these dipoles are quenched, and this is a common view, but it's not. Now we understand that this is not true. Actually, you don't need the atomic spin orbit to unquench this part. There can be interaction, there can be lowering the crystalline symmetry, and these are the things which I will discuss as a good way to control. But what I want to tell you that these two objects, I mean, actually they are not disentangled, they are connected. I mean, and recently we realized, for example, that you can get a completely new type of phase, a new type of magnetic phase, where electrons they move, they form kind of current phases, broken symmetry phase, where the electrons they move and they carry quadrupole. They don't carry charge. People they have been thinking about okay these loop current phases back to the cuprates. I mean, just charge flowing in the crystal, but this charge can be also as a quadrupole. They can have an orbital structure. It can have a spin orbital structure. It can have also high order multiple structure. And you say, okay, but so what? I mean, this is again is charge. No, this internal structure it can lead to chirality, for example. It can lead to completely new types of effects. I don't have the time to enter that, but I want to touch this a bit because it's something which is really new. And indeed, recently for example, we realized that if you use light and you scatter light on this type of multiple current phases, you can you can first probe very clearly these phases by having a non-trivial spin-dependent and spin-resolved handedness dependent photo emission, which connects also to transport, of course. I mean, this is just to tell you that if you want to think about these orbital degrees of freedom in a more general way, and also in a more general way respect to the spin, then you have to think about this structure which is in your wave functions. And one thing which we also know, I mean, I don't have to touch. Okay, now we know that. So, okay, people have been doing a lot of spintronics, but applying electric field to control the spin. Okay, there are many experts in the audience, and Manchon has contributed a lot on that. And now we know that we can do this. I mean, only with the orbital part, which is one of the goal is to control not the spin currents or the spin Hall or the spin torque, the spin rush bar, spin Edelstein, but to control orbital current, orbital Hall, orbital torque, orbital rush bar, orbital Edelstein. But let me add one other box in this, which it can be also beyond the spin and orbital. You can do this with the multipoles, and I think this is something which is a new frontier in electronics. So maybe, so just as a vision, maybe the next step is to have something which is a multiple tronics, which may get a new spice in the field. Okay, but now my goal is to go to superconductivity. And the superconductivity, I think we have to just stay on two paradigms. One paradigm so to generate currents with the spin polarized pairs. So now in superconductivity, so this is the first, let's say this is the first row. So in the superconductivity, people have been spending a lot of time to do this, converting singlet into triplet by engineering, interfacing superconductor with magnets, all sorts of magnetic states. But also because, I mean, singlet superconductor are the most abundant in nature. So, but this has been really very challenging because when you try to do this conversion, at the end of the day, you had to kill some of the Cooper pairs. So this is not very efficient because you think about, I mean, my condensate is made by singlet and I want to polarize them. At the end of the day, I have to make a flip and this will break it. So and this is, it's been always a trade-off, very complicated to do it. And then the question I want to convince you, why can we do that in a different way? So instead of polarizing the spin, we polarize the orbital of the Cooper pairs. So this is what we already we propose in this work with Maria Teresa and Carmine, and if you think it's actually is quite natural. So you have a spin singlet, but there can be orbital degrees of freedom, and you go from states where there is no orbital moment because the states are quenched, and then you polarize them. You form states where the Cooper pairs have an equal orbital moment, but the spin stays singlet. So this is not doesn't violate any principle of this is allowed. Now the question is how, and since orbitals talk to the so in a sense you go from quadrupoles to dipoles in the Cooper pairs. Again, it goes back to what I told you. I mean, these quadrupoles and dipoles, they cannot be taught in a separate way. Of course, in limits they may be separate, but we want to find a situation where these things they come together. And again, I mean, what we found some recipes, some symmetry things to get that, and this is I will show you that we don't need the magnetic things. I mean, we don't need to break the pairs because orbitals they talk to electric field, to strain, crystal structure. Okay, and what is really nice, you can of course you can see that since orbital moment can be L equal 1, L equal 2, when you combine two of them, you can have a quintet, septet. So you can make a huge angular momentum in these Cooper pairs, keeping the spin being zero. Okay. So now I want to introduce one player which is definitely useful for what we will discuss later. Is that first I want to show you that how you can generate these orbital textures at the Fermi level. I mean, this is a very basic thing. I mean, sorry for being so trivial. Okay, this is usually our starting point in d orbitals, but also p orbital materials. So, and if crystalline potential is very strong, this is our quench orbital states. I mean, with orbital quadrupoles, only orbital quadrupoles. How we can get orbital dipole without any spin orbit? Okay, the way is to reduce the symmetry. I mean, this is now what I want to say. If you go to lower symmetry, if you reduce the cubic, so in the cubic, these orbitals, they talk each other all in one way. But if you go to lower symmetry, so you allow hybridization between states which have a different mirror parity, and then you know that you can directly, using the orbital moment operator, you can show that if you, for example, you break the horizontal mirror, states which are, for example, these even orbital MZ and these odd, they hybridize because now they're not anymore protected by mirror, and then you end up to this orbital Rashba coupling. It comes momentum couples to the orbital moment, and then what you have this orbital coupling, which is an analog of the spin, but it has many different. I mean, okay, these are just a series of papers where this has been discussed. Now I think it's well accepted. I mean that so that if you break symmetry, crystalline symmetry, you can induce these orbital textures at the Fermi level, and there are many specific things respect to the spin Rashba. There is no Kramers degeneracy. This interaction can be controlled by crystal field splitting. There are effective mass which are orbital dependent, and you get these textures on the Fermi level, basically. So if you switch on orbital moments, you have your electronic structure at the beginning. So your states are only quadrupole, and then you go to states which they have these orbital dipoles, these arrows, they show the direction of this orbital moment. And okay, so you have these textures. Now we come to the question. So suppose that I get these textures at the Fermi level. So can I mean, this texture means that I can polarize my electronic states. I can generate orbital currents. Okay, I don't want to enter in all the other things in the single particle, but now can I do it? Can I do it with the Cooper pairs? So can I generate orbital supercurrents in a superconductor? What are the microscopic requirements? So what is the resulting superconducting state? So here, this is an orbital current sketch. One electron with the orbital moment up goes to the right. So that one with the orbital moment down goes to the left. Here, up and down is in these arrows. There's a clock, anti-clock. Otherwise, the charge, the quadrupole will not tell you what is up and down. And if you have pairs going in opposite direction, electron pairs, these are all, they rotate in opposite direction. Can this be achieved? This is our question. So the point of view, so from a symmetry point of view, I don't need to have an exotic pairing. I can pair electron on the same side. This is what is called S wave. I can make a spin singlet. And now, again, I can have, if you want, quadrupole Cooper pairs, purely quadrupole Cooper pairs in spin singlet, and purely dipole Cooper pairs in spin singlet. So in a sense, here, my electrons, they have states where the quadrupolar correlation is maximal, there is no dipole. And here is the dipole is maximal, there are no quadrupoles. And these are two extreme cases, which in any material will never be realized. They will come somehow together. I won't like to tell you in more details that. So how to realize that you can get, what are the features, the signature of this type of Cooper pairing, where the orbital moment can be the same in the Cooper pairing? So you do a little bit of algebra. You take your states with a 1. For example, let's take L equal 1, which means the 3D orbitals, this T2G, or you take 3P orbitals. So these are states with a 1 plus minus 1 Z. And this is the combination in terms of the configuration, which they are only quadrupoles. Then you write your operators in terms of your basis. A, B, C is the basis with the orbitals only with only quadrupoles, and this plus 1 minus 1 is a combination that. And now you write the pairing operator, where you have two electrons with the same orbital moment. So then you write down this d daga, if you want 1 and d daga 1, you make an algebra, and you see that this depends on the correlation. So your high orbital moment is basically expressed in terms of pair correlation of the quadrupoles. But look at the structure. It contains the intraorbital, same orbital, but also interorbital. So actually, you realize that without this interorbital part, this orbital moment Cooper pairs is just trivial, basically. It doesn't contain any feature. So all the key aspect of this to have a non-trivial, if you want orbital moment Cooper pairs, you need to generate this interorbital pairing. So pair with a different orbital character should be linked. So this is the analog of having a non-trivial textures at the Fermi level. So how to do that? Let me show you the simplest model it can generate this type of pairing. Is a model where you can start from a type binding model where you have a nearest neighbor hopping, just this conventional quadrupole orbital dependent hopping. Then you have a term which is what I introduced before, orbital Rashba coupling, and which breaks inversion. And then you can have what is also very crucial is another term, which is basically breaking vertical mirror and rotational, twofold rotational symmetry breaking. So, breaking inversion is not sufficient to generate this interorbital pairing. You need to have a lower symmetry in terms of vertical mirror and twofold rotation. So, which of course can be induced by internal. It can be linked to the point group of the crystal. It can be induced by external stimuli. And but what we want is interorbital channel to be active. So if you do the calculation, so you put that in a model and you do self-consistent, I mean, BCS theory. So here I'm just sketching, I mean, this result. I mean, so two things are one thing I want to show you is that, of course, if you break this vertical mirror, when you introduce these terms TM here, then your textures, they are not only in the plane, but they also acquire an out-of-plane component, this LZ part. So this is related to the fact that you're breaking a vertical mirror and twofold rotation. And you see here that without this T term, your interorbital pairing are all zero. When you switch it on, I mean, when you have a small one term like that, you have for example, you activate this BC, which is one of the interorbital pairing between XZ and XY. So, and okay, this depends on the strength of the orbital Rashba coupling. So now let's see how it looks like these high orbital moment pair in momentum space. So this is really nice. So you can basically evaluate, I mean, the anomalous pair function in momentum space, I mean, around the Fermi line, and you see that there are non-trivial amplitude of your high orbital moment pairing. Now I want to go back. You see this pairing is intrinsically complex as a phase, which is related to how much is the intraorbital and interorbital pairing. So this makes a textures in so there is an internal phase which is linked to the orbital pair correlation, and you can see that you generate a lot of pi pairing domain walls or pi vortex, I mean, in momentum space. When you look at Kuiper pairs having equal orbital moment along X, Y, or Z. So I would like to highlight this structure in momentum space of these kind of merons you get, and this boundary where there is a phase change. So there is a lot of pi phase change. And then you say, and we also here you see there are a lot of texturing around the Fermi lines, and these are key signature of these orbital moment Kuiper pairs. And what we claim that since there is a phase which is k dependent, of course you can naturally think that when you put in the device and you generate, I mean, these Kuiper pairs with non-trivial orbital moments, you will get these non-trivial phase texture momentum space with some k dependence in your Kuiper pairs Josephson process. And okay, I don't have the time to go there, but you can get 0 pi phi junction just without any magnetic element. So basically, this is really driven by applying, I mean, intrinsically the material has these low symmetry terms. You apply maybe a strain or an electric field, and you generate these textures. When you link the two superconductor with different textures, you will get some anomalous phase in the Josephson process, and this will give you a very interesting pi phi or zero junction, which are of course of interest for many things, which I don't have the time to touch. So then I go back to the paradigm I was telling. Okay, there have been a lot of work, people trying to use singlet mixers and trying to generate spin triplet Kuiper pairs, right? Sorry, I'm putting the hand, but And so this has been developed in many works. I mean, to generate this long range spin triplet correlation. Now, so what we want to propose is a new type of a paradigm where you have a superconductor, you generate high orbital moment Kuiper pairs, and then you have a Josephson supercurrent, which is orbital polarized. And in principle, this can also be used to torque, I mean, a magnet. This would, I mean, these Kuiper pairs, which they carry a high orbital moment. This is, in this case, is a quintet. So, and a lot of these is a strong pair amplitude at the Fermi level. They can, of course, I mean, be used to couple to spin moment, I mean, magnetization, to spin orbit, whatever, I mean, but so you see that this is potentially interesting. So now I want to make a step forward, which I also think is very interesting. So if you have if you can generate, I mean, high orbital moment Kuiper pairs, so you have an orbital moment, two electrons, which non-trivial orbital angular momentum, also locally, I mean, can you imagine that this this orbital supercurrent, can it be that you get a vorticity? So this, I want to touch this orbital vortex now. So basically, why you expect that you get this vorticity? Because again, I mean, this Kuiper pair structure has an internal dependence. Now I go in the real space, and the orbital dependent correlation, this diagonal part and the off diagonal, they make a real and imaginary part. So there is a phase which is intrinsically generated by the orbital dependent correlation. And you have these two plus and minus, I mean, possibility in a time Russell invariant superconductor. They are both, I mean, there. But one can go clockwise, the other one can go anti-clockwise. So Kuiper pairs with plus can make a vortex, and with minus anti-vortex, which means at the end you will have a orbital supercurrent flowing. So you see that the question is whether you can generate, I mean, a type of vortex state without breaking time. So, and we did that. We took the model I showed you before. We did a real space calculation, full self-consistent. We put this orbital Rajba, we put the terms which break vertical mirror and twofold rotation, and you get a stable solution with respect to the uniform phase. And now you see that the amplitude of this vortex is completely different what you have in an Abrikosov vortex type. In an Abrikosov vortex type, the core is zero, and all around there is something which is more or less homogeneous, which can have this tiny parabolic dependence. But here you see you have a large amplitude. I mean, there's a strong anisotropy of this vortex state in the order parameter. I mean, so you can have a large amplitude in a portion of and then it will be very small all around on the other side. It's strongly nematic, if you want. I mean, and then I was telling you, okay, you have this orbital current, right? If you have these vortices, you should expect to have this orbital supercurrent flowing. We calculate, I mean, we introduce this orbital current operator, and we look at this around the vortex. The vortex is here, and you see that that there is this vorticity of the orbital supercurrent with the different component around, I mean, around the core. Of course, this is a very exotic object. I mean, it's not, you are not breaking time. Is purely generated by orbital correlation, and it wants to get some orbital supercurrent flowing around the core, which has to carry naturally all this anisotropy. So how this can be, I mean, in our case, it came from is a stable solution, is a free energy stable solution by simulation in real space. I mean, a full self-consistent BCS calculation. And this is shown here, but what we think that this, and I want to tell you, this is a very interesting view. This is a sort of vortex anti-vortex, because one type of Kuiper pairs, they go clock, and the other one goes anti-clock. So there are two vortices which are entangled by the orbitals, degrees of freedom. And since we need to break to lower the symmetry, it can be intrinsically in a crystal, but you can also drive by external sources. You need electric field, but you also need a gradient, because the gradient, they naturally break the vertical mirror and twofold. And this is actually the analysis of the free energy, the stability of this vortex phase. And you can either go in this direction with a small electric field, for example, strain, but you also need a gradient. This probably is making a challenge in terms of experimental way to generate this object. And then you ask, okay, but why? So what are the hallmarks of these states? This is a new type of state. You need a low symmetry in the crystalline part. So you can induce, you have this vortex and anti-vortex, but these are neutral. So these are supercurrents, they are not charged. So this means that when you apply supercurrent, you will break this vortex and anti-vortex. You will get anomalous flux coming from nothing. So in the superconductor. And now you can ask, okay, why you expect this to happen? Because actually we know from electromagnetism, moving dipole generate an electric field. So if I apply an electric field, or if I lower the symmetry to have some electric field in the superconductor will tend to screen it by generating vortices, which they are neutral supercurrent with orbital supercurrent which are polarized, okay? So how to measure? One thing which might be that you apply this perturbation, or you induce this symmetry breaking, and then you come with a tunneling STM, and you should see vortices with this phase, not the conventional vortices. Or you will see all these anomalous flux response when you apply any tiny time rest symmetry breaking, because you have a vortex and the vortex. Any tiny symmetry breaking in time will dephase them, and they will get some flux generated. I mean, so then let me give you this view, which I like it. I mean, so superconductivity, magnetic field, and electric field. So we know magnetic field will make a breakers of vortices. So what happens when you do something with the electrical means without generating currents, like reducing the symmetry, strain, crystalline potential? So what we propose is that we generate vortices, which they are basically neutral. They can be this vortex and the vortex. I mean, object which with the orbital supercurrents, orbital moment supercurrents flowing around the core. So this somehow, if you include these orbital degrees of freedom, and you include the possibility of generating orbital moment Cooper pairs, you may reconcile some kind of symmetry between the electrical field and the magnetic field in this system. Okay, so I want to mention that this type of concept can lead to very interesting way to make no reciprocal effects, because what I showed you, that this electric field or strain can make this anomalous vortex phase, will change supercurrent amplitude. This will make a diode by what we propose by back action supercurrent. So you have a current, you change you have electric field or gate, you change, I mean, the quantum state of the superconductor, but the supercurrent is modified, and this supercurrent can, as I told you before, I mean, it can modify again by this vortex state. And when you do this back action, you can generate a no reciprocity, because the back action will change the parity of your current phase relation. So I don't have time, I mean, to go into detail, but if you're interested, I mean, you can look at this work. And the other thing is that these high winding vortices, because these vortices which are not just winding by 2 pi, they can also be a natural object to give a no reciprocal response in a superconductor. So these things, they just can be used for detection, for example, but also for functionalization of these orbitronic effects. Okay, now I want to go to the orbital Edelstein effect. I mean, if you apply supercurrent, I mean, in a superconductor, in principle, as in a metal, you can induce, I mean, if inversion is broken, you can induce a magnetization. So this is a conventional magnetoelectric effect proposed by Einstein in metals or in other materials. You can find in also in superconductor. So what we did, we asked, okay, can we get something when you look at the orbital part? I mean, so this is what we analyze in this in a context where basically you don't have a spin orbit, but you have only orbital degrees of freedom. You break inversion. You have this orbital rush-back coupling, and the response to the current. Now the supercurrent enters as a gradient in the phase of the superconductor, so differently from a metal, and this will give you, I mean, an orbital moment in the plane, for example, in a C4. In a C4, I mean, configuration. So this orbital moment will be in the plane, transverse to the current, Ly, and so what are the key features? I mean, respect to the case of the spin rush. I mean, so as I told you at the beginning, I mean, so the orbital rush-back coupling does not have a Kram's degeneracy and can be tuned by many other ways, I mean, without breaking time. So you can control the mass of your orbitals, you can control the splitting of your orbitals, I mean, just by modifying the crystalline environment or applying external perturbation. And you see here, this magnetoelectric susceptibility can be controlled in amplitude. I mean, if you change the effective mass, for example, and the chemical potential here, or even in the sign. So you can change the orientation of the induced orbital accumulation by, for example, modifying the orbital splitting. So here you see that it's negative, it goes to positive, and is very suppressed, it goes again positive. So this is a first, very important aspect is that the other one is, I didn't show you here, but is that the magnetization you can induce is 2 order of magnitude bigger than what you get in the spin. So even in the superconducting state, and this is also partially linked to the orbital moment, orbital moment I was mentioning before. When you apply the current and inversion is broken, you generate this correlation, which can enhance the accumulation of orbital moment in the superconductor. But another interesting feature is that you can generate, I mean, if there are defects in your superconductor, phase defects, weak link, around this defect, your orbital accumulation will show, it can have basically some modulation in sign. So you can make a defect which is in a superconductor, and you will see that the Einstein effect will have an opposite sign around the defect. I mean, it can be changing from positive to negative. So like here, you see this is a positive, or you have this negative positive sign change. And so this is really something unique of the orbital Einstein response. And depending, of course, on parameters in the model, but that if you have this defect in the superconducting phase of your superconductor, I mean, you can have an accumulation which can be either, I mean, homogeneous or non-homogeneous. So in principle, I mean, this might be interesting to be measured. So again, you can look at with some squid, and if you have if you make engineering of these defects, you can have this orbital accumulation with opposite sign around the defect. Maybe you can also apply some gating or strain to amplify this orbital accumulation, and you can switch from in plane to out of plane. You can change from having these anti-parallel domains to parallel domains. So there is a kind of magnetic control of this effect. I mean, which is quite unique in the orbital part. Okay, I want to now, Aurelina, how many minutes I still have? I mean, do I have 5 minutes or 10 minutes more?
Yeah, definitely 5 minutes, no worries. Yeah.
Yeah, 5 minutes. I want to also connect to again to the fact that when you have these you reduce the symmetry, you use this pi pairing in the orbital channel. I mean, and I want to highlight the fact that if you have three orbitals, I mean, and two of them they go pi, this generates frustration. So this pi pairing is usually has been discussed in the context of iron-based superconductors or other unconventional superconductors. So here, what I want to highlight is that you can generate this pi pairing by using orbital Rashba coupling. So again, what we thought that okay, that suppose that you apply or you have a strong inversion symmetry breaking on the surface of a superconductor, and these will convert in the orbital Rashba coupling intralayer. So we make this a kind of a layered analysis again in a BCS type of approach, just S-wave spin singlet multi-orbital states. And you also include this interlayer symmetry allowed coupling, which also couples to the phonons, I mean, in the other direction. So then what you find is that you can induce, I mean, two type of a pairing. One is that this pi pairing, so the phase between the orbitals in the channel A and B and C, they go opposite. So, or you can also induce this kind of density wave. So there is, if you go along the superconductor, the sign of the pairing change. I mean, you have some sort of pair density wave, and this is coming as mainly from these interlayer orbital lattice Rashba coupling, and you have this pi phase, pi z, this pair density wave phase, and you can tune by just controlling the symmetry breaking on the surface of thin superconductor. Okay, so very quickly, I want to close with these Majorana and topological things in the interorbital part. So this is just a very quick message. I mean, people, they think, okay, that I get Majorana with the P wave spin triplet, but you can also do with the S wave without any P wave pairing, but having interorbital. Again, this interorbital correlation between the different orbitals. If you pair up electrons with different orbitals, and you have a local spin triplet, you have all sort of topological nodal superconductivity, edge states, Majorana, flat bands here. So I don't have time to enter, but so you can also look in this work. So again, I mean, the message is that if you have a system where the interorbital pairing are dominant, this can make a topological superconductivity without any P-wave pairing. And this is probably interesting and applicable to materials where disorder will kill odd parity pairing, but you can still have some spin triplet. And of course, with a strong spin orbit, this will also link to the other orbital moment co-pairs I mentioned before. Okay, with this, I want to just conclude and come back to my starting point. I mean, so I try to convince you that there is a way to shape, I mean, superconductivity by controlling the orbital degrees of freedom, going beyond the quadrupoles, beyond the charge in the dipole, and these you can have a high orbital moment Kuiper pairs, you can have vortices with the polarized orbital supercurrents. All these orbital things, they naturally contains pi pairing. They have some pi coupling which emerge when you have this multi-orbital and you include orbital Rashba and you reduce the crystalline symmetry, which means that there is a lot of phase frustration, which can also lead to novel type of quantum phases. I don't, maybe, high order, I mean, condensate, other things, I mean, and so I want to say that you can have a topological states which are completely linked to the orbital part, again, which S-wave topological phases, which they don't require, I mean, a P wave or high angular momentum in the block dependence in the block K vector. Orbital Eisenstein effect can be giant with respect to the spin part. These things can lead to exotic. I didn't have the time to talk about orbitally polarized Andreev scattering. So usually you always think about Andreev scattering where you just change spin up goes in down. But now you in all these zoo you can think about scattering, Andreev scattering, which of course are active. I didn't have the time to touch it, but in all these Josephson supercurrent, I mean, under process, they will include a conversion between quadrupoles and dipoles and all these things which will enter, generate high harmonics, which is good for non-reciprocal effect. You can have all these phenomena. They are kind of related to each other, and we really hope that we can develop more. So there is a part of materials which, unfortunately, I cannot touch, but for the time limited time. But of course, I mean, most of the superconductors which are more interesting are multi-orbital. I mean, and one needs really to find the right condition to generate these phases. At least this is a hope. Okay, the people involved in this talk. I mean, many things I mentioned. I mean, the people in Salerno, Maria Teresa Mercaldo, Carmine Ortix, and Claudio Guarcello. So also things on many interaction with the people with Luca Chirolli. Now he's in Firenze, and Francesco Giazzotto in Pisa, and his group, and Yuri Fukawa. She was in Spin, and now he's in Okayama. So there are many ongoing orbitronic projects with Gabor Xive, who is also here as a postdoc in Salerno, with Tom Sanderson in Mainz. Also, I didn't have the time, but interesting issues of generating spin triplet correlation by Eisenstein effect, and Luciano D'Onofrio, who is also working on spin and orbital filtering, and we are these quadrupole current, I mean multiple currents phase, and we are trying to merge with other interesting phenomena in superconductors. And this is project acknowledgement, and I thank you for your attention.
Thank you very much, Mario. It was a very exciting and very inspiring talk. A lot of very dense and very exciting information. Do we have any questions? You can either, okay, I see there is somebody has raised a hand. Let me see who has.
I think it's Manuel.
Yes, Manu, yes.
Yeah, Manuel, yeah.
Yeah.
Hello, everyone. Hey, hello, Aurélien and Mario. Thank you, Mario, for
Salut, Manu.
very nice, very inspiring presentation. So, I think I have a basic question. So, which materials could display this fascinating phenomena that you're describing? I'm thinking maybe KT111 because they have these broken mirrors, vertical mirrors as well. So, can you tell us a little
Yeah,
bit?
I think that okay. So what we're doing with we are doing with Gabor. I mean, yeah, working on both elemental material 111 with so and with the application of gating and strain. I mean, so we have okay. Soon, I think we will come up with some interesting effect should appear. I mean, so this will work for yeah niobium, vanadium, and all elemental superconductors. I mean, but of course also oxides can be a very good candidate. I think that so KTO and also so they can. I think that they can host these phases. I mentioned. I mean, there are all the symmetry and orbital content to generate these these things. I mean, and other materials also which we are now considering is this this kagome and other 2D materials. I mean, we are trying to look at that TMD materials. I mean, they also have the right players to generate this stuff. And so we would like to make, let's say, some clean prediction. I mean, from an experimental point of view, because of course there is a lot of complexity and many effects can come together.
Yeah.
So yeah, but definitely KTO can be a good candidate to. Yeah, for example, I mean, the point. So I don't know. I mean, so it would be nice if you can try to design. I mean, maybe you can already do it. I mean, something that you try to make some torquing with some orbital supercurrent. I mean,
But maybe we should talk separately because this is super exciting, I think.
yeah, I think so definitely would be nice to have more experiments trying to see whether this is all or not only theory, imagination.
Okay, thank you so much.
Thank you, Manuel. Yeah,
Bye.
thanks.
Yeah.
Okay, do we have another question? So either you can write it in the chat or just turn on your microphone. Otherwise, I will jump in. I have a very basic question about the kind of the symmetry the symmetry of the wave function of your pair. So I understand it's so it should be antisymmetric, right? Because it's a fermionic pair. So then if you have a singlet, then it means that your orbital content should be symmetric. Now, if you have the Rashba effect, I would expect the orbital content to be at least partly antisymmetric. Then this should actually favor the triplet, and this has a connection with Tom. So it's really my naive vision, but I would like to hear you on that.
Yeah, I think that is a very good point. I mean, you make actually it's really as direct as I'm telling you. You have a spin singlet is odd, right? And then you have a equal orbital moment, which is even.
Yeah.
So your Cooper pairs, and so the antisymmetric part is from the spin singlet.
So
and
when
it must be
you mean equal orbital moment?
So you can have either you can have equal quadrupole.
Oh, they have the same dipole also, and the same
Or the same dipole. So so far people have been always thinking about singlet equal quadrupole, which of course are even under exchange. But you can also have even dipole, same dipole, right? So again, I'm going back to this. Okay, maybe the introduction was a quite
no, it was very clear. But
yeah, I think it's clean. If you think there are quadrupoles and there are dipoles, and people will say, okay, conventional things. If you don't have any orbital moment like orbital Rashba, you want to pair electrons with a equal quadrupole because there is no dipole, there is no gain. I mean, to any energy gain. But if you're at the Fermi level, you have already dipoles. Then you can also pair electrons with the same dipole. So now, if you look a little bit, so this will be a basic intuition. But what we realize, I mean, is that this is not sufficient. You need to have a little bit of extra lowering because you need to activate this interorbital pairing, which otherwise by symmetry will be killed. And then again, you go back to the quadrupole. So in a single particle part, you have a less constraint to generate these textures. In the pairs, so you have a more constraint that you need to get rid of other symmetry transformation, which are not impossible. Yeah.
So I cannot, what I had in mind was the paper from Gorkov on Rashba.
Yeah.
Right. And if I remember well, but again, I'm really new to this field, is that what they show that you can actually have a triplet state in the presence of Rashba.
Right.
So of course, if you take a step back, I would say, well, if we have an orbital Rashba, then we should have all the same symmetry constraint. But perhaps I'm missing something because what you're saying is that the orbital Rashba itself is not sufficient. Now, is the spin Rashba, how is the spin Rashba in the Gorkov Rashba paper different?
Yeah, because the spin Rashba, you don't have the orbital, then you go in the spin triplet, but you need to have odd parity.
You directly work on the spin.
Yeah, then when you go to spin triplet, you need the antisymmetric part is in the momentum in the sign is odd parity momentum. You have a structure factor which takes care of that. So which means this is also you can go there, but this will be high harmonics in the pairing, which will be fragile to disorder, will be very so requires some unconventional
Okay. Okay.
momentum dependence of your Coupe pairs, which of course they are also generating, I mean, high order things in the anomalous part. But the leading term is that we don't want to have pairing, local pairing will make S wave.
I
So
see.
you don't want to have you don't want to go to a high order channel in the pairing, which usually requires unconventional glue. So like spin fluctuation, orbital fluctuation, which might happen, but this already, makes everything a little bit more exotic. Yeah.
I
So
see.
in this case, if you stick on the local vision, so you have either spin triplet and orbital singlet, which is what I showed you that can give you topological Majorana without P wave, or you have a spin singlet and orbital triplet, orbital quintet, orbital whatever. I mean, equal orbital, or singlet and quadrupole in the orbital. So these are the three animals, right? You can have it, and in the S wave locally. Then of course you can play around and have you can change the orbital part by modifying S wave in P wave or D wave and blah blah blah, right?
I see.
So you can compensate the symmetry. It has to be antisymmetric by using the spatial extent of your pairs, which goes also in the direction of having things which in this very 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 part which emerge. But okay, it's a story which of course expands in many directions. But if you stick on the basic, if you stick on the lowest level of formation of orbital moment, this is this is what you need. And
I see. I see. Uh, perhaps you can take one last question. Otherwise, I have another one.
yeah, sure.
Is there any? Okay, nobody is raising the hand.
No.
And I have one last question, which is probably even more naive. Um, can you get D-wave superconductivity from the orbital texture? Because you end up with a gap that is K dependent naturally, right? I mean, your gap function
Sure.
becomes. So I would say, well, probably this orbital texture is simply the natural route to get D-wave superconductivity, and then probably also P-wave, by the way.
Yeah. Okay. So let me make one comment. Actually, so I'm starting by using this Vanier states pairing, right? But at the end of the day, I mean the band pairing. You go on the band. You go and you look at the pairing in your at the Fermi level in the bands. So now, of course, you generate. I mean, as I showed you, these textures. They have all these merons which there are there are many places where there are nodes in the band picture. So you see what I mean. So if you start with these trying to form these high orbital moment pairs, when you go in the band picture, since your electrons they has orbital Rashba coupling and they have also these other symmetry breaking interaction will appear in a shape, I mean, which is really not S, not D. It's a very is a Meronic like because this vorticity and the orbital moment and the fact that you have orbital textures in the orbital Rashba in a single particle, they combine to give a lot of nodes,
I
which
see.
in a sense, which is not D wave actually. So it's a very unconventional in the
I see.
so you would expect to say so if I write everything in terms of these equal orbital moment pairs, I will see a pairing amplitude which has a nodal structure which is like Meronic with the textures which are very structured. I mean, so it's not D wave, it's not P wave, it's not S wave
I
because
see. Okay.
also
Okay.
because it's a vector, right? So it's a D vector like, it's like for spin triplet, but now with the orbital moment, and they have a textures which like it kind of combines the orbital Rashba and this
I
is a
see.
signature of this pairing, right? And this is
Okay.
why when we looked at this Josephson transport, you get is a pi, phi, all these weird coupling, right? It's coming from this internal phase, this orbital dependent phase.
It really enriches the landscape. It's amazing, really amazing.
Yeah, this is, I think that it would be very nice to find a kind of material case where you can really look at this by close by. I mean, it's
But I think Manu probably has interesting ideas. So I'm really looking forward for the next discussions.
Okay, yeah.
So thank you so much, Mario. Really appreciate it.
Ariel,
it was a very nice work.
Okay.
And
all the
thank
best.
you, everybody. And so we're looking forward for the next one coming up next month. I get back to you about that. Thank you so much.
Thank you, Ariel. Thank you, everybody. Yeah. Goodbye, everybody.
Bye-bye.
Bye-bye.